So welcome, Professor Bobby Reiner from Institute for Health Metrics and Evaluation, and thank you for getting up so early in the morning to speak to us. Yes. Fantastic.
Yes, thank you very much for inviting me to present, I guess I'm going to call it the version 4.0 of our model. So my name is Bobby Reiner. I'm Associate Professor in the Department of Health Metric Sciences here at University of Washington, and also part of the Institute for Health Metrics and Evaluation. I want to go a little quickly through the first couple slides, just so I can kind of get a little bit more to what we're currently doing as opposed to what we started doing closer to 2.5, 3 months ago. Seems like years ago. But at any point in time, please feel free to interrupt with questions, because I'm happy to clarify any of the points of what we did in the past as well as what we're doing now. I need to advance my slides now. So back in February, we were asked whether or not we could estimate, just for the University of Washington medical system, when they think they might have the surge of people coming in, and maybe how big the surge would be relative to their own capacity to deal with people coming in that just need treatment versus people coming in who need intensive care versus people coming in who need ventilation. We started working on an extremely simple model for them. It became, I guess, known around a couple of the medical systems that we started doing this. So we started getting some requests. Some of the medical systems actually were across states, so then we started estimating more and more states, and then we kind of felt we were in for a penny, so we might as well go and try to estimate all US states. From there, our first forecast was March 24th, maybe it was March 21st, one of the two. And we've been just kind of building from there. It's gotten a lot more attention, and of course the original purposes of the model have been somewhat superseded by questions about what's going to happen later in the fall, and to try to account for both some of the assumptions that we made in the model that had some pretty optimistic usages of movement mandates, to try to account for the fact that people are releasing mandates possibly or probably, and in some cases very likely way too early, as well as a potential for a second, third, and fourth waves. We've been building on the model, and at one point in time we had to make a bit of a leap away from our old approach to what I'm going to present as our current new approach, and we're still iterating 7 days a week. What we're trying to do now is to account for resurgence in the second wave, while forecasting forward what we think is going to happen as a function of things like mobility, increased testing, and again the implications of listing the social mandates. I seem to have a hard time moving the slides. So there's a huge amount of information that's coming out, and a lot more than there was 2.5 months ago. But one of the premises of the work that we started doing was that we just inherently thought that death data was more reliable than case data, given wild biases, especially early on in testing, availability of testing. Certain areas were only testing people who traveled, and they wouldn't even look for community transmission, so it's not surprising it'd be hard to find it. But death data we hoped would be a little bit more reliable. From there, we also didn't have, without testing, we can't do things like testing and treating or really good contact tracing. So instead, we were trying to look at the effect of different non-pharmaceutical interventions, and specifically at the time, just different restrictions on how people are coming into contact with each other, whether it's reducing any gatherings at all, or closing schools, or having to stay at home orders, and trying to match that with changes in transmission. And so just as an example, sorry, a lot of this is going to be US centric, but we've as people hopefully or probably know, we've clearly moved out of the US. So for example, the stay-at-home order, there's a huge variation when different states have implemented the stay-at-home orders, and to be fair, some places haven't. Just one little bit of nuance when I say places haven't. To be able to compare across locations, we had to take relatively strict definitions of the implementation of mandates. And so as I go through this, it should kind of be, we have a team of people trying to collect information, get as much an up-to-date status across countries. But if somebody kind of suggested or alluded to the fact that maybe people shouldn't have, let's say, non-essential businesses open, but they just kind of said, oh, it'd be better if maybe the ones that don't have to be aren't open. That's not really the mandate, as opposed to a governor or an elected official getting up and saying this is a decree. And so we had to then, given that we were having these issues with sometimes people kind of get the hint of the mandate without actually having the mandate officially implemented, we looked for other measures of on-the-ground activity. Another good example was here in Seattle, where it was kind of the first epicenter of the outbreak for the US. Every metric of mobility based on cell phone data or Google movement, GPS movement, they all showed that there was reduction in travel even before the mandates started kicking in. So we wanted to try to account for that. The first model, which in some ways is a bit infamous, is this curve fit model. I just want to go quickly through this. I'm not going to make excuses for it because it served its purpose. But I want to also point out that if people have very nuanced questions about this model, I'm happy to take them. But we're moving pretty close to being able to move entirely away from it. But for the purposes of that model, though, we were making this observation. I think a lot of people were making a similar observation that there's a somewhat similar trajectory. If you look at the overall death rate, the cumulative death rate. And here, this is a figure from a couple months ago, where the blue line is the cumulative death rate in China. The x-axis is days since the outbreak hit a death rate of 0.3 per million people. And you can kind of see, if you stare and you believe and you cross your fingers, that maybe all of these curves are kind of going up, and maybe they're going to all kind of come over the top. Obviously, if we have something where we have more exponential growth due to unchecked transmission, we might expect it to not peak out like this. But one of the assumptions that we made early on was that as the outbreak continues in places, people would hopefully take steps to reduce transmission. So then we got into the business of trying to understand these curves. At the time, the only curve that really tells us what happens at the tail is the blue line, which is China. But we have some places in Italy that were starting to come closer to hitting their peak. For the purposes of the simple analysis of trying to figure out when and maybe how high the magnitude of the outbreak would be, we considered basically curves that are going to look sigmoidal. We have the Logit family of curves, and we ended up doing a bit of out-of-sample testing to see which curves fit better, and the curves more related to the error function seemed to take a better fit, and so we kind of ran with those functions. There's a couple very clear issues with those functions. The first of which assumes that you basically have a symmetric distribution in terms of the outbreak. Whatever the shape looks like on the way up, it's going to look the same on the way down, both in terms of how it looks, but also in terms of the timing. A couple really nice aspects from the mathematical standpoint for the functions. Of course, it's quite easy to take derivatives, and then therefore it's quite easy to find maximums. And so it's a bit easy to manipulate the function. So we could use it and then start maybe trying to add in some other components. But using that, we were able to try to get some good estimate of when we thought that the peak would occur as a function of some covariates. So obviously, if we have a place that's just growing unchecked, there's no real great signal in that individual curve that it's going to stop, other than somewhat common sense or hope. Or we could try to borrow more from a mechanistic mathematical models, where we know it's going to come down eventually when we hit herd immunity, but one would hope we're not waiting that long. But what we started to do is we started to see what was the curvature of the curves looking like in the places that were a bit more advanced, as a function of when mandates were in place in those locations. And so using that, we could then say, okay, once a stay-at-home mandate was implemented, it's 2 to 3 weeks from that point to the peak of deaths. Something like that analysis would then say, okay, this place just implemented their stay-at-home mandate, therefore we have another 2 or 3 weeks until they hit their peak. So we were looking across a number of different mandates to try to play that game or fit those relationships to help predict what we thought was going to happen. I have to put it in bold, a very critical assumption of the model, which was, again, a bit naive, but in several different ways, was that everyone would eventually impose the mandates and then they would keep them on through the first wave. And so, you know, while we made that assumption, we try to put it front and center. I think a lot of times people would make the, would miss that. Maybe we didn't put it in big red letters in the front, but you know, that was part of the assumptions. And so when people didn't put mandates in, or as people only put some of the mandates in, they were obviously instantly breaking the assumptions of the model, which at the time was, you know, something we knew we were going to eventually have to start dealing with. And so let's see if I can get the thing to actually move forward. In some places, this did pretty well. We were looking in terms of places that kind of hit their peak. We had a number of examples in Italy where the dots are the daily and log daily death, and the curve is what we get by fitting this error function. This, of course, is going to then assume that on the way down, it's going to look exactly the same as the way up. The results that we came out with in the middle of March pegged the total number of deaths in the US around 80,000, as one would hope, making estimates into July that we had pretty wide uncertainty. Estimated, again, under the assumption that people are going to keep all their mandates on, that we were going to be able to have death rates dropping below the kind of threshold where we started modeling, so 0.3 per million. And this was a wide variation when we thought that was going to happen as a function of what the transmission looked like in the place and how many mandates they had already implemented. So I guess I could stop for a second and see if anybody has any questions on that. It's in the space of COVID timelines. It's a bit of history, but happy to take a question before I move on. I'd be happy to move on, but don't want to just skip over it. Okay, I got one shake of a head, so I'm going to keep going. So from that point, as more places experienced their peak, we could use more information. So as the model built, more places experienced their peak. We could keep blending that information in. Obviously, only one place had an outbreak for 4 months, but you know, other places had outbreaks for 1 or 2 months, and so we could start using a lot more information. We did also start noticing that a number of places didn't satisfy a number of the assumptions of our model. One of the things we wanted to start trying to do was there's been relatively idiosyncratic patterns in death reporting by location. Some places, they don't have a lot of deaths over the weekend. And then they possibly for reporting purposes or reasons. And then all of a sudden they have a huge spike on Monday, and we have to figure out how do we want to distribute those deaths, assuming that maybe they didn't all happen on Monday. Some places it happens on Tuesday. Some places they kind of do catch up, where once every couple of weeks they collect a bunch of deaths that didn't occur in hospitals and just spit them out into the system on one day. So we started trying to figure out how to incorporate deaths and cases and hospitalizations. And then probably more pertinent moving forward, and possibly a better discussion point for this group, a group of us had been for a while advocating that we should probably consider that the right tail of these outbreaks is not going to be symmetric. We want to maybe consider the kinds of curves you get out of dynamic transmission models. And by doing so, we could also start looking at what we think would happen if transmission intensity rebounded in a more natural way than if we fit a statistical curve that lets it go back up. So we developed and then implemented an SEIR model that accounts for all future transmission is based exclusively on the SEIR model that uses mobility testing, temperature, and density. And so we take a hybrid model where we blend the two, where we use the curve fit at the moment to still kind of guide what we think the data looks like today and up to a week into the future. And then from there, we splice over into a SEIR model. So one of the reasons we had to do this was there's a lot of places that did not have symmetric tails. So this is a bit of data for Madrid. Pretty clearly, assuming a symmetric tail is going to cut off and underestimate what we think is going to happen. a lot of places had a pretty curious effect where they actually, the tail, for all intents and purposes, actually looked relatively symmetric, but it didn't start immediately after you hit your peak. And so a lot of places appeared to have kind of a lingering effect where maybe our effective was bouncing around 1, or more realistically, possibly we're trying to model an entire large location at once, when in fact we're having a lot of small outbreaks going on. And when I do the aggregate of all those small outbreaks and try to pretend it's one well-mixed system, we get a pattern that looks curious. And that's another hypothesis that makes a lot of sense. And that's somewhat of a hint of where we're trying to go with our model 5.0. Finally, we had some examples, some unfortunately good examples in the US of places where, albeit small number states of deaths, but places that were clearly on the increase, already releasing mandates. And so for better or worse, this is the red line is basically data from Iowa. Again, small numbers of deaths, but they released their mandate, some of their mandates on May 1st. They wanted to, I guess, be first out of the gate. And so trying to account for all these things made us have to rethink a little bit of our approach. One of the other things that we were doing, or what was happening at this time, was obviously we're collecting a whole bunch more data. A lot more data is just coming out, and so we can be a lot more informed about what we think the relative patterns of infection to fatality are across different ages. And so one of the ways we started to do this was we can get case fatality rates, and obviously case fatality rates, depending on how you define a case and how you're hunting down infected people, might be quite a bit higher than an infection fatality rate. But if you have a closed community like a cruise ship, for example, or you start to do a lot of active case detection, you start getting case fatality rates that get closer and closer to infection fatality rates. We also started leveraging more of the information that was coming out that there wasn't a huge bias in age in terms of infection probability. Obviously, there's a huge effect of age on the probability of severe outcomes or death, but there wasn't as much evidence, and at the time, the evidence looked pretty much like you're equally likely to become infected if you are 20 versus if you're 80. Interestingly, as more serological studies are now coming online, we're going to try to adjust that a little bit, because maybe there is a little bit of evidence, at least in some of the places that are doing serological studies, that the under 10 might actually have a slightly lower probability of infection. But you know, one location, one survey, we have to take all of these things with a grain of salt. And so trying to try to be a little bit more careful about the age structure of infection to fatality allows us to be able to invert what we think is going on in terms of deaths back into what we think is going on in terms of infections, which then opens up a somewhat easier way of modeling infections with a mechanistic model, as opposed to trying to get into the business of accounting for varying case reporting rates and then using cases in some much more complicated model. Again, we started getting a lot more mobility metrics. They don't all agree. Sorry for the size of this plot, but the left panel is different mobility metrics in Washington relative to baseline. So the dashed line is business as usual. Some of these metrics say that movement, depending on how you define movement, are you saying you're going to work, or are you just leaving your home, or are you traveling a certain distance? Different sources were giving us different information. Sometimes those are consistent. Lombardia, the different movement metrics are consistent. But we're trying to figure out how to incorporate that into a single measure of mobility change since February 15th and use that in the model. When we do that, we can then start playing a little bit more of an informative game of how well does changes in movement match changes in the mandate. So did a movement occur, change before a mandate came or after a mandate came? And could we say, okay, well, what do we think would happen if you release this mandate in terms of movement, and movement specifically? We do then able to play the game in the other direction, saying movement change, transmission intensity seemed to change. How well did that correlate? It's a discussion I think was being alluded to earlier, and it's a discussion that we and many other people are having, whether or not removing a mandate is going to have the same effect as implementing the mandate, not in terms of movement, but now that people are doing all these other things like distancing or wearing masks, we don't necessarily expect the same rebound in terms of transmission intensity, but we can start looking at these things. We then, of course, have places, places in the US are a good example where people are removing their mandates while there's still a good evidence that transmission is circulating, and we're already, to some extent, starting to see the impact of those things. Finally, we're trying to account for a lot more information. One of the big things is testing. Testing is first going to expose more cases and more infections, and so more testing might make it look like there's a worse problem, and our esteemed leader thinks that maybe it's a bad idea to test more people because then we'll identify more cases, which is brilliant. But that being said, it also might be able to be used to remove infectious people from the population, identify them and identify their friends and family, contact tracing that might actually become another intervention in the very empty toolkit that we have. And then finally, again, just because we're having, we're waiting longer, we'll have a lot more information about what does a peak look like, what does it look like on the way back down, and can we start to figure out why some places are sharper, some places aren't, some places last longer at the peak, some places don't. So one of the things that we tried to do in the death space of the model is start to take into consideration that the cases aren't maybe as big of an issue as they did before. Maybe they're becoming a little bit more stable, or at the very least, maybe relative to their own measure, they're stable. So if I say cases are going to be biased in a particular location, but are the next 8 weeks higher, or next 8 days higher than the last 8 days? Even if it's biased, maybe there's a trend that we can learn from. And so we started trying to borrow that trend to get a little bit further out into what we think is going on in terms of deaths. And then from there, again, we have to be very careful. There's huge issues in terms of huge spikes in death reporting. Some of it obviously is that there is a distribution of time from when a person gets infected to when a person dies. It's going to be a function of all sorts of things: when and if they sought treatment, comorbidities, what kind of treatment they were able to get access to. But again, the reporting ends up being a big issue, so we have to worry about smoothing the data. And then finally, dealing with this issue in this curve fit way of extending the peak or having a long tail. We loved our error functions, so we stuck with error functions, but we then basically used error functions as basis functions, and then basically did a spline regression using them as the splines to try to get an extended peak. And this also will allow us to get a bit of the asymmetry depending on the weights we put on the various splines. But then the kind of the next direction we've gone, and we are going to continue going as an SEIR model. So I'm going to try to go a little quickly through all this because I see I'm already 22 minutes in. But so I'm not going to say what an SEIR model is, but we have two infectious components because there's a good amount of evidence that first, people might not be PCR positive until they're into their infectious stage. So if I'm going to be using testing as one of my measures of transmission or possibly an intervention, I want to be able to separate out those that actually would be able to be detected from PCR versus those that might be contributing to transmission. The second reason is there's also a good amount of evidence that there's even for those that eventually become symptomatic, there's a pre-symptomatic phase where they're walking around feeling fine but infecting other people. And so there was two different reasons that we put two different infectious classes. We also, you might notice very small there's an alpha term. Again, we're fitting large places in aggregate, assuming a well-mixed model, which is obviously wrong for many, many different reasons. But to try to account for the fact that we are not really modeling one population, but entire states, and in some circumstances, entire countries at once. We put an alpha term to kind of dampen the effect, to account for the fact that we're not well mixed. So the model approach is basically take what we think are deaths from the death curve model, convert them into infections by delaying them from using a distribution about time from death back to infection using the infection fatality rate. From there, we fit an SEIR model. From there, we get in a transmission intensity. Well, we're matching or tracking the beta term in the transmission intensity. We then try to regress or understand the change in that through time as a function of a change in a bunch of covariates like movement, density, temperature, testing. We then try to forecast those covariates. Some of those are very easy to forecast. Densities, hopefully not going to change. Temperature, there's an entire field of people that are in the business of doing that. Testing is obviously something that we a bit more hypothetical. We then take the forecasted covariates, plug them into the regression, get forecasted betas, put that through the SCR model, and we get a forecasted outbreak. We then convert that back into deaths. And that's the current approach to try to account for uncertainty. We're doing this deterministically at the moment, the SCIR component of this, but to try to account for uncertainty, the deaths that get converted into infections that get fed through the model, they have variation from the original curve fit model. And so the whole thing ends up being done by draw. I point that out because we do this by 1,000 draws and we're up to, I think, 160 locations. And so we have a whole math team that we're able to work up algorithms to take the original model, which would take me 3 minutes to fit, and now they can do 1,500 fits in 2 minutes, which is pretty incredible. One of the ways they do this is by playing a bit of a game with solving the system of differential equations by actually just fitting a smooth to new infections, because that's the data that's coming into the model, and then from there running just 3 ODEs just directly through, not really solving, well, not at all solving them, just running them through, then doing a bit of algebra at the end. It's a nice approach. At the moment, we were using an assumption of concavity. So like California, you can see goes up, comes down, but now that we're in places where it's no longer doing that, we have to be a little bit more careful about that first spline. That's one of the things we're at right now. I mentioned the regression. We put the regression in. I'm going to start going a little faster because I want to get to a bit of the results. Mobility. And then from there, we're able to get curves that look, well, at least they're not extremely certain about what's going to happen in August. And so that's something that I think nobody was really happy with the original models. And so the whole thing goes through quite quickly. So we were able to repeat this over and over again to play more and more experiments. One of the things, so the current projection for the US, 143,000 deaths by August 1st. Obviously, well, this is under the assumption that all the mandates that are currently on are going to stay on. All the mandates we know are going to come off when we know they're going to come off, which is obviously a bad assumption. So we have to update this. We're now trying to become in the business of forecasting when people are going to remove mandates, but that's a exercise. But we have moved out of the US to try to estimate this for other places. And this map will be growing substantially over the next 2 weeks as we move into India and Pakistan and South Africa and a number of other states. But we're trying to account for some other biases in data, so we can actually do it for lower middle income countries just writ large. One of the things we get to do is we can then say we have an effect of the mandates, we have effective movement on transmission. We can then say, what happens if I remove one of those mandates? How do I think that that's going to affect mobility? And then how do I think that's going to affect transmission? So we can say, where are you in your outbreak? Do you have a low R effective? Do you have enough room in your R effective to remove a mandate? Increase transmission a little without letting the outbreak occur. So for example, in this particular draw in California, we have an individual timing of when we could remove different mandates, assuming that this is exactly the right truth, and assuming that the effect of the mandate going off is the same as the effect of the mandate going down, not on mobility, but on transmission. We can say when we think the timing of the different mandates could be removed. Then we have other states where, for example, in Ohio, the effect of school closures was pretty massive on mobility. Therefore, it ended up being massive on transmission, and Ohio never seems to get low enough in their transmission by the end of the fall or the end of the summer to allow them to have space to bring back school closure, although they wouldn't open schools possibly until the fall anyway. But these are the kinds of questions we can ask. We can do the whole thing by draw, so we can start getting uncertainty on when it would be advisable to lift different mandates. I'm getting closer to the end. Obviously, this is one way of making that life choice about balancing the economics with the health. R effective of 1 is actually a pretty scary thing when you start allowing for stochasticity and measurement errors across the board. And so maybe a more risk adverse governor might say, I want to only have a certain fraction of more deaths. Can you work up a scenario? And that's kind of what we're working on. So we're trying to move entirely away from curve fit to just directly use cases, hospitalizations, deaths, and testing data. So we still have a bit of some assumptions that go into the model. Obviously, there are more intervention strategies than just mandates. We're trying to incorporate those. Tons of other covariates we'd like to incorporate. We're trying to move to every location that has greater than 50 deaths and high quality cause of death data. That's step one. But then step two is really trying to move into places, sub-Saharan Africa, for example, where the death data itself is going to be biased, and so we can no longer leverage this. Well, the death data is better than the case data, so therefore we probably think we know what's going on. So we have to be a lot more careful about things. And so obviously a lot of different issues. But with that, I'm hopefully have a couple minutes for questions. But thank you for your attention.
Thanks very much. If you could, Martina.
So thank you, Bobby, both for agreeing to give this talk in record time. And it was a great talk, really. I've been wanting to see what's behind the curtain for some time. So this was very helpful. So a couple of things. First, you know, everybody attacks the assumptions, but the thing about assumptions and models is that they tell us what would happen if. And so they're really just ways of leveraging sort of computation to answer complex questions, basically. So thinking back on version 1.0, which made this assumption that every place that started its lockdown would keep its lockdown until it needed to, you can almost argue that that gives you a baseline for what might have been possible if you had followed this policy all the way to its conclusion faithfully. And then everything that happens above that is sort of an excess death, which is a cost of reopening. Is that discussion happening in your shop, or does nobody want to touch that with a 10-foot pole?
So there's a queue of things we want to look at. At the moment, the resources that are working on COVID aren't funded on COVID. So a lot of us are trying to actually keep our day jobs going as we do this. Some of the people have just transitioned over entirely, but that is more along the line. We have like a list of like postmortems that we would like to do. That is squarely in the postmortem space. It's a bit of a tricky political issue in terms of we do seem to have some traction at the different levels of government in terms of we're not one of the groups that's just not being listened to at all. So we might, you know, so putting out something like that now
may not be the
might
time.
hurt that, but I mean, realistically, I think we would if we had the human resources.
But you could almost turn it around to, so here in Washington State, where I think you obviously have the ear of the governor, and the governor I think is a rational man. In a sense, what you're offering now is a metric for what it's costing us at each stage, right? So here's what we might have been able to obtain, and here's kind of where we are. So instead of saying this is your fault, it's really just a metric for how much is it costing us to relax these restrictions, and that might be a useful metric for them.
Oh no, absolutely. And so I guess to kind of allude to kind of answer the question. So I had to go through it very quickly, but in those the mandate release slide, there was two colors. The first color, the top color was when R effective was less than 1, but not far enough less than 1 that you could remove a mandate. And so that's a cost that you're paying economically by not removing a mandate. And then below that, there was more the salmon, I guess, color that represented the extra transmission you were allowing by removing the mandate. And so there's exactly that balance.
Okay.
I think one of the reasons why it's a little tricky to go back to the beginning is because the model, trying to forecast what we think is happening, given that we know there's some issues with the old model we had as well, makes it a little like what reality do we pretend we're in if we want to make that postmortem? Do we pretend we were back in the beginning of March where we had a very limited amount of data, or do we pretend we actually knew what was going to happen, fit the model there, and then play that game out? And so it's probably much easier to do the second thing than the first thing, but that's not really quite fair for the people who are making the policy decisions at the time. But it's definitely something that I think is relevant, and it is something that we should be doing.
Thanks. Do we have one more question? Because we
All right.
then perhaps need to get on to our general discussion
I guess I do if no, oh, Peter does, good, go ahead.
I'm Peter Traman from Stockholm University, Sweden. My question is a bit about the mathematics of the model. So when you show the SEIIR model, implicitly or explicitly in that model, you assume that there are exponential times until people recover. It's an ordinary differential equation.
Absolutely.
For some, it is known in theory that that assumption might have quite big effects. Did you consider making that a bit more? I guess it comes at a small cost to generalize that the distribution to something more realistic.
Yeah, so that's extremely well taken. That is, it is sometimes a bit of a struggle to change. So going to an SEIR model at all was definitely an effort. That is 100% accurate. I'm trying to continually remind people that we have a whole bunch of exponential distributions going on. So people are shooting through these classes quite fast, where we know some of them don't, they have actual lags. That's more on the developmental side, but there are other teams, obviously, that are worrying much more about the exact distributions, and we're trying to, at the very least, make it, do the boxcar trick to at least make it so that we don't have so many people flying through in the beginning. But realistically, there's other people that are saying it's not just going to be a gamma. It actually has a particular shape, and we should use that particular shape as we move forward. And so that's something we're trying to use. Again, doing it 1,500 times makes it if you make it a second longer, it does end up really starting to add up. But it is something that we're aware of, and it is also something that at least as we start putting out manuscripts associated with this work, which is I think something we've really not done a great job of doing. Those are the kinds of robustness assessments we need to do, where we say, what happens if you change that distribution? Do you get a wildly different result? And if you do, well, we should probably be couching what we're doing much more carefully. But yeah, it's extremely well taken, and I'm fully aware that we're making some pretty strong assumptions in that space.
Thank you very much.
Okay, thanks. I think we need to leave that there and move on to our general discussion. So thanks very much for coming to Cambridge, Bobby, and we hope you'll take some interest in the further parts of the program as we're here till August. So thanks.
Thank you very much for inviting me.
Okay.